Okay, welcome to the lecture 33 of this course, Classical Mechanics 1. So, in last lecture we have studied the Lagrange multipliers method and how one can apply this for system where you cannot eliminate the constraint, or when you need to know the constraint force. So, today we will have a tutorial class, but before that let me recap what we have studied in this context of Lagrange multipliers method and how to deal with system with non-holonomic constraints. So, let me recap few things. So, when you have that constraints cannot be eliminated, so when constraints netted to find independent variables, or we need to find the force of constraints then we need this Lagrange multipliers method, as I mentioned. Particularly when you have non-holonomic constraint, you cannot eliminate your constraint to find independent variables, and in the variational principle, in Hamilton's principle or in the D'Alembert's principle, if you do not have independent variables, then there will be difficulties. You cannot compare both sides. So, that is why we need this method, and in this method if you have the constraint of this form, say non-holonomic constraints, and it can be velocity dependent. So, dqk plus dlt dt equal to 0 in this form if the constraints are, because this is velocity dependent. A, Lk and Lt, they are constraints, they are function of coordinates and others. So, and L runs from 1 to number of constraints, I consider M last time. So, when we consider virtual displacement, this was changed to ALK delta QK equal to 0. So, if you have a constraint of this kind, delta k is virtual, and if you have the Lagrangian which has del qi, qi dot and t, then through Lagrange multipliers method we have derived that equation of motion can be written is del L del qi minus ddt of del L del qi dot plus lambda L sum over L A L I equal to 0 for I equal to 1 to n. So, this will be the equation of motion. So, we know all the L, K, L, I coefficients from our constant equation, and then we can write the equation of motion. The lambdas are known as, lambda is Lagrange, lambda is Lagrange player, and we know the physical interpretation of this Lagrange multipliers. In last lecture we mentioned that they are related to, these lambdas are related to the generalized force in the system. Okay. We will consider more example in this tutorial class, in this lecture 33 is tutorial class. So, in that class, and then we will see how to use this equation for one constant, how to use for this equation for two constant kind of things, okay, and how to find solution. So, we will consider examples to learn this. Okay. So, this much we have done in last class, and in the last class also we consider an example, and in that example we were trying to show this last point, that lambdas are related to the force of constraint in the system. So, for that we consider the example. So, let us consider that example again. So, example 1, that a particle moves on a horizontal table under the constraints x square plus y square equal to a square. That means some particle is moving on a surface of a table in a circular path, and we will show for this. We have shown actually, but I was in hurry in last lecture because of time, and could not emphasize the points I wanted to convey. So, we need to show that lambda for this problem, the Lagrange multiplier is proportional to the centrifugal centripetal force exerted on the particle. Okay. So, that we are going to show. So, first we will find equation of motion. So, let me write the Lagrangian. For equation motion you need to write Lagrangian and constant equation. So, there is no potential energy because it is moving on a horizontal table. So, assuming that table is 0 of the potential energy. So, we have Lagrangian x dot square plus y dot square, and constant equation I can write x dx or x dot plus y dot equal to 0. That means, according to my notation, Ax is x and Ay is y. So, now let us use the equation del L del x dot x minus ddt of del L del x dot plus, there is one constant. So, there will be one lambda. So, nothing to sum here over lambda. So, it is x equation. So, lambda A x will be 0. So, if you calculate, this term is 0. So, only we have this term. So, minus m x double dot plus lambda x equal to 0. Exactly similar way, if you calculate the y equation, it will be m y double dot plus lambda y equal to 0. Okay. And also I mentioned that in last class in detail, that after finding this equation you need to use the constraint condition also. So, we need the solution will be given by these two equation as well as the equation of constant, that is x dot y dot equal to 0. Okay. So, let us recall that this equation is 1 for today, and this equation 2, and this equation is 3. Okay. So, if we differentiate equation 3 for calculation, you will get x double dot plus y double dot plus x dot square plus y dot square equal to 0. That means, x double dot plus y double dot equal to minus v square. Okay. Because x dot square plus y dot square is v square, velocity square. Okay. So, let us denote this equation as the equation 4. Now, we have to calculate, from this we have to find what will be the lambda, and lambda we have to show is proportional to the centripetal force exerted on the particle. Okay. So, to use the equation 4, let me multiply this equation 1 by both side by x, plus equation 2 we multiply by y, and we obtain minus m x double dot. So, let me erase this minus x. So, let x double dot plus equal to okay, x double dot. So, let me write plus m y double dot equal to lambda x square plus y square. Okay. Okay. Now, I used from equation 4 x double dot and y double dot. So, I can find my lambda x square plus y square is nothing but m v square, right, minus v square. Okay. So, but x square plus y square is a square. So, lambda is equal to minus m v square by a square, implies lambda is proportional to m v square by a, which is nothing but the centripetal force exerted on the particle. Okay. So, this was the point I wanted to convey in the last lecture, but I was in hurry. So, we will consider more example today, and for that we will find that that will give you the illustration of the theory we have learned in this section. Okay. So, next problem, example 2. Example 2, let us consider another problem. So, let me write a hoop of radius a rolls on an inclined plane. Find out the velocity of the hoop. At the bottom. So, let me show you the explain this problem in terms of diagram. So, if you have a inclined plane, so this is your inclined plane, and some hoop is rolling along this surface. Okay. And suppose this angle of inclination is a constant angle phi, and if this hoop rolls down to the bottom, then what will be the velocity when it reaches the bottom, that you have to find. And you have to use this problem you can solve by energy consideration. This can form by considering Lagrangian, and also using this Lagrange multipliers method. So, we will solve this problem using Lagrange multipliers method, and just to illustrate the problem, this method we have learned. Okay. So, let us consider that our x direction is along the inclined surface, and in any time the position of the hoop is x, position of the hoop x from this reference point, and this is the height. So, height, and this will be then L minus x, remaining length of the inclined surface, and A is the radius of the hoop. Okay. So, constraint, okay, I forgot to mention that the hoop is rolling without slipping. So, it's have a only rolling motion. So, it is not slipping. So, this constraint constraint will be a theta dot equal to x dot. So, the rate of rate of rotation, angular velocity theta dot will be related to the x dot, the velocity along this inclined surface will be this for the constraint that is rolling without slipping. Okay. So, now first thing we have to construct. So, we have found the constraint condition. So, let me write x dot minus a theta dot equal to 0. So, let us, this is my equation 5 today's lecture. So, this is equation 5, and you can find your a x in our notation is 1 and your a theta is minus a. Okay. Okay. And now we have need to know the Lagrangian. So, Lagrangian will have, it is, if m is the mass of the hoop, then x dot square, and the kinetic energy for the translation motion and the kinetic energy for the rotational motion half m square theta dot square, and then the potential energy minus the potential energy. So, if this angle is phi, so this length will be L minus x times sine of phi, height. So, height is L minus x sine phi. So, potential energy will be mg L minus x sine phi. Okay. So, what will happen? Okay. So, this is Lagrangian, we have constant equation. So, let me write, this is my equation 6, and now we find equation for x and theta. So, for x equation will be del L del x minus ddt of del L del x dot plus lambda, only one constant. So, there will be only one lambda times a x equal to 0. So, if we find this equation, we will find that del L del x will contribute from here. So, minus minus plus, so it will be mg sine phi, and then ddt of del x dot will be m x dot plus lambda times ax is 1 equal to 0. Okay. So, this equation is mg sine phi minus mx double dot plus lambda equal to 0. So, let us denote this equation by equation 7, and then we consider the theta equation. So, theta equation, del L del theta, there is no theta dependent terms in, look at the Lagrangian. So, phi is of course constant, so it is nothing to do here. So, you will have first term is 0, then you will have ddt of del L del theta dot will be m square theta dot, right, because look at the Lagrangian, half m square. So, differentiated 2 theta dot. So, this will be and theta double dot, okay, and then lambda times a theta. A theta is minus a. So, minus a lambda equal to 0. So, m square theta double dot equal to minus a lambda. Okay. So, what will happen that lambda, we can write lambda equal to minus m a get cancelled from both sides. So this A theta double dot. So let us consider this equation 8. Okay. So now we get in terms of we need to find the acceleration along the inclined surface x double dot. So if we substitute this lambda in equation 7, so putting lambda in equation 7, we obtain that mg sin phi minus m x double dot lambda equal to minus. Okay, we also have to consider we also have to consider the constant equation that we have not considered yet. So let me put first lambda equal to m square theta double dot, but theta x dot and theta double dot has to be related, okay, to find the x double dot. So this is equal to 0. So let us equation 9, but we also have to use the constant equation, which is equation 5. Equation 5 says, so equation 5 says x double dot equal to a theta double dot. Okay. So a theta double dot is your x double dot. Okay. So this equation 9 implies that mg sin phi minus mx double dot minus mx double dot. Okay, a theta double dot is x double dot. So this implies the x double dot is half g sin phi. Okay. So once we find the acceleration along the inclined plane, so now you can find that the velocity will be starting from that hoop start at the top position with 0 velocity. So it will be, the velocity can be given is v square equal to 2x double dot L. If L is the length of the inclined plane, then this will be, so v will be 2L times g by 2 v square will be sin phi. So v will be root over GL sin phi. So at the bottom, because x equal to L will be the bottom, so at the bottom this will be the velocity. So I asked you to find the same solution from the conservation of energy, obtain the same solution using other methods. Okay. Okay. So in the remaining time on the tutorial, today's tutorial class, what we'll consider an example where we can have two constraints in the system. Okay. So let us consider another problem. This problem we have discussed earlier also by direct method, but let us try to find equation of motion using Lagrange multipliers method and illustrate the method with two constraints. So let me write the example 3, this problem. So let me write the problem first. A particle of mass m is free to move on a smooth wire whose equation, the equation of the wire in cylindrical coordinate is given by, so there are two constants. So one will say cylindrical coordinate, the where equation is given rho equal to a, and then other condition is z equal to b phi. Here is you see that we are using the cylindrical coordinates rho z phi. Okay. So find equation of motion. So what you have to do, find equation of motion. Using Lagrange multipliers method. So we will solve this problem. This problem will give you two important things, information. One is that using cylindrical coordinates for this type of problems, and second is that it has two constants. So the system has two constants. So first step, we need to write that constant in the desired form, right? Rho equal to a, constant can be written as d rho plus d. So let me write a rho a. Okay, I have two constants, so I have to be little bit careful. So let me write proper notation. So constant equation d rho, I can write a 1 rho d rho plus a 1 phi d phi plus a 1 z dz equal to 0. But we do not have a rho equal to a, does not have phi or z. So this I can write a 1 rho is 1, a 1 phi equal to 0, a 1 z equal to 0. Okay. So this is from the first constant. Now in the from second constant, z equal to b phi. So let us write this as the our equation 10. Equation 10. So this equation 10, and then we will have the other constant. Other constant is z equal to b phi. So z equal to b phi can be written b d phi minus. Okay, I will write in the same rotation 1 2 rho d rho plus a 2 phi d phi plus a to z d z. Okay. So equal to 0. So when rho in this equation we doesn't have any rho, so 2 rho will be 0, and so phi will be a 2 phi will be b, and a 2 z will be minus 1. Okay. So now we have to, so this let us denote as equation 11. What will be the Lagrangian? Lagrangian will be L equal to, in cylindrical coordinates, half m rho dot square plus rho square phi dot square plus z dot square. Now it is very straightforward to find the equation of motion. Because of lack of time, I'll probably will stop here, but you can very easily use, and maybe in the beginning of next lecture I'll mention how to find this constant, and then we'll find and move to the new topic. So this plus, now there are two lambda, so let me write lambda 1 a 1 rho plus lambda 2 a 2 rho equal to 0, and del L del phi, just let me write the equation and I will stop. Del L del phi dot plus lambda 1 a 1 phi plus lambda 2 a 2 phi equal to 0, and similarly for z. So, let me stop here, and in next class we will move to the Hamiltonian formulation. So, that will be the lecture 34. Okay. Bye for now.